All right, let's get on with tutorial 3, where we'll discuss learning to learn, what is known as meta learning. In the previous tutorial, you saw that joint training works, but it has issues. It doesn't respect the sequential nature of distribution shifts, right? Which happens in the world. Also, training takes a lot of time because you're throwing in all the data you have at the same time. And to learn all the distributions at the same time takes time. And the notion of concept shifts just don't agree with joint training. The idea with a concept shift is that the same input has to return a different output. For example, in the case of when should we plant tomatoes in the year, because of climate change, that output is changing itself, and how the input to output relationship is changing. So if you do joint training, you have to decide, like, what do you want? Do you want the pre-climate change mapping or the post-climate change mapping, right? And so that joint training inherently cannot deal with, but we want that. We want a model which works now. We can't do joint training unless there is a way to somehow cue it that we are dealing with now as opposed to later. But that just adds more complexity. We can deal with this problem much more easily, as you will see now. But yes, we are probably asking too much of our model. We want one model to do multiple things, but that's what we want. So let's see how we can get it to do that. So this is where we come to the notion of meta learning. So the idea is, now instead of talking directly about learning like everything at the same time or sequentially, we will focus on one level higher. So learning to learn. Like, can we become good learners in the first place? Can we create good learners in the first place? And so I mentioned we because humans also learn to learn. We are actually good at it, and at this point at least. But for kids, we have to teach them how to learn to learn. And so, how would that look like in machine learning setup? That's what we'll discuss now. We are going to explore an algorithm called MAML, model agnostic meta learning. So the intuition is that, so you have a single network that is trained to perform multiple tasks, right? For that, you would have different task specific weights, presumably, because it has to perform various tasks. So what MAML does is that it has a shared set of base weights, which probably could be like shared features across tasks. And then you have task specific weights that are learned on the fly. So for each new task, you could just learn those task specific weights, whereas your core network is stabilized. So it does not forget everything from the past either, right? Or does not forget the things that are relevant for other tasks. So training a model with MAML looks like the follows. So there's an inner loop and an outer loop. So the inner loop is what is traditional training, right? So you have task specific weights, and then you initialize the model weights as the task specific weights plus some base weights, right? Which are initialized in the outer loop. So let's say just some random set of weights that are initialized now. Then you have a random set of task specific weights. You add them to those base weights for different tasks. You do it differently. And then you have your loss for that task and you just update the task specific weights, right? And then this can be done sequentially now for each task T. So you train first on the task one, then you train on task two, then you train on task three. So just training the task specific weights. As you can see, like, it doesn't do anything to the base weights because the base weights are constant. And so that can help you with some sort of, like, integration over time, or like not leading to catastrophic forgetting, kind of dissociating the different task specific weights. So you train those task specific weights, right? And then you freeze the task specific weights, right? And then you update the base weights, reduce loss on all tasks at the same time. So this is now joint training. But if you think about it, this is basically us trying to get to a nice set of base weights such that now we can add any new task specific weights, and we'll just be able to learn faster without destroying performance on previously learned tasks, right? In the outer loop, we optimize for base weights given all tasks. Then again, we initialize with those base weights, and then we can go back into the inner loop and then train on new tasks. So we can continually update how the model should learn to learn, right? So what this is doing in task space or weight space is that we're finding base weights that are a good starting point for learning each of the individual tasks quickly, right? So let's say initially the base weights were like here, blue, right? These are, like, let's say, two weights in the network. We are plotting their values. So let's say the base weights are here, blue. And then for task one and for task two, we trained the task specific weights and we got some loss. And it's not that great because we are in a random part of the landscape and you can't really go too far, right? Given a particular amount of training epochs, let's say. Now you jointly optimize over the two tasks, these base weights, right? And so now this lands up in another point in this weight space. And now from here, if you train the task specific weights, probably you'll get a better loss because this was jointly optimized. The blue was jointly optimized across the tasks, right? So now it will end up in a part of space where like nearby points map on very well to different tasks. So that's the idea of MAML. The blue training, the training of the blue set of weights, the base weights, is the outer loop, and then training on the individual tasks constitutes the inner loop. So you will play with MAML in this tutorial. So the way you will do that is we'll apply MAML to the fruit price task. So we'll create a couple of distributions. The function that defines the fruit price, which we created previously, will just vary the parameters to create different distributions, right? And this represents concept shift because on a particular day the output is changing. Also, the entire function is changing. So what the network has to do, the function mapping is changing. So there's three different functions the network has to map onto, right? And we are not going to provide all functions at the same time. We'll provide them one at a time, sequentially, right? So how would you do this? And so we can use MAML. And so you'll see that once trained, your model would be able to quickly adapt to these different functions. So the training to get to a good local minimum or a good performance on fitting a new distribution will be super fast. That will not affect any performance on previously trained functions. That also solves the catastrophic forgetting. So that's what we'll deal with in this tutorial.